Welcome to this explainer. Today we're putting on our physicist hats to map out a literal engineering roadmap. We're going to look at exactly how humanity can transition from our current earthbound limits to capturing the staggering, immense energy of the sun itself. It's a journey from macro-level thermodynamics to the awe-inspiring engineering steps required to finally leave our planetary cradle.
Here's our roadmap for today. We'll start with the Kardashev scale, then look at the earthly energy bottleneck, move into solving the mass problem, dive into orbital AI and solar, and wrap up with moon bases and mass drivers. All right, part 1, the Kardashev scale. So, devised by a Russian astrophysicist, this scale measures a civilization's technological advancement using the ultimate objective currency of the universe, energy. It basically categorizes a civilization by its thermodynamic limits. Type 1 harnesses the available power of their entire planet, Type 2 harnesses their home star, and Type 3 their entire galaxy. And humanity? Well, we're practically nowhere right now. We capture such a tiny fraction of Earth's power that we don't even fully register as a Type 1 yet. To really grasp the massive leap required to become a Type 2 civilization, just look at this number, 99.86%. Our sun contains literally 99.86% of all the mass in the entire solar system. Of the tiny fraction that's left over, most of it belongs to Jupiter. So from a physicist's perspective, Earth is kind of just this tiny, insignificant dust mote floating in the miscellaneous category. Right now, we use less than 1/1,000,000th of the sun's power output. If we could capture just this number right here, 0.00001, a millionth of the sun's energy, or what you might call a microsol, that would be an absolutely epic achievement for us. To even get on the board and not just single percentage point on the Kardashev scale, we have to exponentially scale up our energy capture. Which brings us to part 2, the earthly energy bottleneck. Now, you might be wondering, if we need all this energy, why can't we just build massive solar arrays and data centers right here at home? Well, thermodynamically speaking, our planet is actually a terrible place to capture solar energy at scale. Compare Earth to space for a second. 70% of Earth is water. Of the remaining land, large chunks are unlivable poles or freezing tundras where you get very little solar power anyway. Plus, running massive amounts of AI compute generates insane heat, and cooling data centers on Earth is brutally difficult. Space, however, gives us unobstructed, constant solar power, and because it's a vacuum, it allows us to effortlessly radiate all that heat away. Space is really the only logical place to build.
Okay, moving to part 3, solving the mass problem.
Knowing space is the ideal location is one thing, but actually building up there is another challenge entirely. The very first engineering pillar we have to conquer is getting mass to orbit. Imagine if we had to throw away an airplane every time it flew. Nobody would fly, right? It'd be way too expensive. The same goes for rockets trying to escape Earth's deep gravity well and thick atmosphere. The steps to fix this are clear. First, achieve full reusability of the rocket. Second, achieve rapid reusability, meaning the rocket lands, gets caught by the launch tower, and flies again without laborious refurbishment. And third, seriously scale up the mass payload we send to orbit. And the physical embodiment of that exact solution is Starship. It is the heaviest flying object ever made. Version 3 has double the thrust of the historic Saturn V moon rocket, and version 4 is going to push that to 3 times the thrust. By flying these rockets rapidly, potentially multiple times a day, we can jump our global payload capacity from around 2,500 tons a year straight to millions of tons per year. Starship is essentially the ultimate delivery truck for the infrastructure of a Type 2 civilization. That brings us to part 4, orbital AI and solar. So how do we actually deploy those next 2 pillars, power and compute? Check out these target values for orbital data centers. We aren't just slapping rocket engines on a brick building here. We're talking about deploying massive satellites with a 70-meter wingspan. They'll use 250 watts per square meter of solar arrays to generate power, and double-sided radiators operating at 1,400 watts per square meter to dump heat right into the vacuum of space. That setup gives you 150 kilowatts of peak power. That's enough to run an entire high-end rack of AI compute safely floating 600 kilometers above our heads, all connected by high-speed laser links. But keep our main goal in mind. We're trying to capture a significant fraction of the sun's energy. A few satellites simply won't cut it. We need a terawatt of computing power in space. And to get there, we need chips, which brings us to the terafab. This is a proposed 100 million square foot chip factory. To wrap your eye around that totally wild number, that is 10 times the size of Gigafactory Texas. It's an unprecedented scale of terrestrial manufacturing required just to feed our orbital ambitions. And the timeline to execute this? It's incredibly aggressive. The aim is to scale our orbital AI exponentially. The roadmap targets pushing 1 gigawatt of AI compute to space in about a year, then scaling up by an order of magnitude to 10 gigawatts in 2.5 years, 100 gigawatts in 3.5 years, and finally targeting an annual deployment of a full terawatt. For some context on that, a terawatt is roughly twice the total electricity consumption of the entire United States, deployed into orbit every single year.
Finally, Part 5, Moon Bases and Mass Drivers.
Now, here's where things get truly mind-bending, because honestly, a terawatt is still incredibly small on the Kardashev scale. Eventually, we'll exhaust our ability to launch all this heavy infrastructure straight from Earth. We have to stop fighting our deep gravity well. So to jump another 3 orders of magnitude, to go 1,000 times bigger than a terawatt, the next logical step for a developing Type 2 civilization is to set up shop on the moon. By establishing lunar bases, we can literally begin local manufacturing of photovoltaics and radiators using lunar materials, taking full advantage of an environment with absolutely no atmosphere and only 1/6 of Earth's gravity. And the true advantage of that lunar environment is that we could essentially accelerate AI satellites into deep space without a rocket. Since there's no atmosphere to create friction and gravity is so low, we wouldn't even need traditional chemical rockets to launch from the moon. We could use a mass driver, which is basically a massive linear electric motor, or a railgun, to physically fire manufactured solar arrays and AI data centers deep into the solar system. I know it sounds like pure sci-fi, but it is the required physics for scaling up our civilization. So we've traced the entire roadmap, from the theoretical thermodynamics of the Kardashev scale, to reusable rockets overcoming Earth's gravity, to orbital AI data centers, and all the way out to conceptualizing lunar railguns. The blueprints are being drawn up right now. The physics are sound. All of this brings us to one final, deeply exciting question. How quickly will humanity execute these engineering steps to finally register on the Kardashev scale and awaken as a true Type 2 civilization? Thanks for joining me on this explainer. I really hope it completely shifted how you view our future in space.